Okay, so yesterday we started working on work energy theorem. We kind of reviewed that work is a change in energy, okay, a change in mechanical energy to be specific, okay, and we talked about how that could mean a change in potential and kinetic energy, both in any given situation. Okay, so what we have to remember is that work can equal force times distance. Okay, if the force and the displacement or the force and the distance are in the same direction, then theta is 0 and we don't even need the cos of theta part. Okay, and that's the way it is most of the time, including the question here. It's being pushed down a ramp, right? The force is down the ramp, the displacement is down the ramp, they're in the same direction, so theta is 0, right? But we also have to remember that work is not only force times distance, it is also the change in mechanical energy, okay? Meaning that force times distance equals, okay, our final mechanical energy, so that would be EP final plus EK final, because that's how we calculate mechanical energy, add potential and kinetic, minus EP initial plus EK initial. Okay, and then obviously we have formulas for potential and kinetic energy. So this would be mgHf, okay, plus 1/2 mvf squared minus mghi plus 1/2 mvi squared. Some cases, one or more of those forms of energy may be 0, okay, depending on the situation that we are dealing with. So in this question here, a car is being pushed down a 15-meter long ramp. So the ramp is 15 meters long. All right, so we have to envision how this looks. So this side is the 15-meter long side. It says that when it gets to the bottom, or sorry, at the starting point, the car is moving at 1.2 meters per second. So that's up here, okay? It's moving at 1.2 meters per second, and it's 3 meters. So this side here is 3 meters higher than down here, which is the final position of the car. Okay, assuming there's no friction, so we're not losing any energy to any what we call non-conservative forces, okay, what would the speed of the car be at the bottom of the ramp? So we know it's starting at 1.2 meters per second, 3 meters higher than it is down here. What we have to do is figure out how fast is it going at this point. All right, so think about this stuff here, okay, that work equals the change in mechanical energy, and see if we can figure out what the final speed of the car would be. That's what we are looking for. All right, I'm going to give you a few minutes on that. This is about as tough as a work energy theorem question would get for Physics 20. Okay, let's have a look at this one. So the thing we have to realize to kind of start this question off is that because the car is being pushed down the ramp, it is going to have more mechanical energy at the bottom than it has at the top. Everyone okay with that? Okay, it has a certain amount of mechanical energy at the top because it's moving and it's above the bottom. But it's also being pushed down the ramp, which is adding mechanical energy because it's work. So at the bottom, we'll have more mechanical energy. The thing I'm looking for in this question is part of the final kinetic energy. It's actually the final velocity here. That's what I'm looking for in this question. All right. So one of the things I want to look at is, first off, are any of these 4 forms of energy 0? Okay, well, I'm 3 meters above the bottom of the ramp initially, so I have potential energy at the beginning. Moving at 1.2 meters per second at the top of the ramp, so there's kinetic energy initially, right? We're looking for the final speed of the car, and it would be faster at the bottom, so we definitely have this stuff. Do we have any of this? Is there any potential energy at the bottom of the ramp? No, because the height at the bottom of the ramp is 0. All right, so I can eliminate that from my equation, which means I have to move less stuff around. All right, so I've got force times distance. Okay, the work done by that 450 Newton force over the 15-meter length of the ramp, okay, is equal to 1/2 mvf squared minus the initial mechanical energy. So can I take this stuff here and just bring it over to this side? Can I bring like the initial mechanical energy over here? right? Really what I'm looking for is the final mechanical energy. So the work plus these two things here should tell me the final mechanical energy, right? The work plus whatever energy I started with should be the final energy. Everyone all right with that logic? Okay. All right, so we've manipulated the equation. Now we have the final mechanical energy, which is all kinetic, off on its own. I don't want to find the final mechanical energy. I want to find out what's the final speed. Okay, so what do I have to do with the half and the m? If I want to move something, I do the opposite. So what's the opposite of multiplying? Divide, right? So I bring them over here. So I've got 1/2 of m over here. That leaves me with vf squared. I don't want vf squared. I just want vf. So I'll square root. Okay? Now this will give me the final speed of the box or car, or whatever it is, at the bottom of the ramp. They tell me the mass, so I've got that. Okay, now I can put in all of my numbers. All right, so the force is 450 newtons. The length of the ramp is 15 meters. So there's my force times distance, right? Plus my initial potential energy. So that'll be 1500, the mass of the car, times 9.81, the acceleration due to gravity, times the height of the ramp, 3 meters. And I'm going to add on to that the initial kinetic energy. So 1/2 times 1500, the mass of the car, times 3 squared, the initial, sorry, 1.2 squared, right? What was it at the top? 1.2, right, sorry. Okay, the initial speed there. Then I'm going to divide all of that by 1/2 times 1500, and then I'll square root the whole thing, and that will leave me with the speed at the bottom of the ramp. So is this kind of like the roller coaster questions that we did before? Okay, it's kind of like those, except I also have a bit of energy that's being added in on the way down. Whereas in the roller coaster questions, it was always the energy at the top and the energy at the bottom were the same. Okay, so when we're plugging this in, so we're going to go 450 times 15. So there's the energy I'm adding by pushing the car. Okay, not a lot, but it's some. And I'm going to add on to that the potential energy at the top. So 1500 times 9.81 times 3 meters. Okay, and then I'm going to add in the initial kinetic energy, 0.5 times 1500 times 1.2. Oh, that's why it seems so small. 450, good eye, times 15 meters. Okay, plus, that's better. 1500 times 9.81 times 3 meters. Okay, plus the kinetic, 0.5 times 1500 times 9.81. Nope, sorry, not 9.81, times 1.2 squared. What is going on with this thing? 1.2 squared. All right, so there's the total energy at the bottom of the ramp, right? The total energy at the bottom of the ramp. Now I'm going to divide that by 750. That's half of 1500. All right, there's my speed squared. So I'm going to square root that. All right, so the speed of the car at the bottom of the ramp is going to be 8.3 meters per second. Okay, that's about as involved as a work energy theorem question would get for Physics 20. Right? Really, still a lot of that is intuitive. There wasn't really a lot of difficult math there. Okay, the hard part was figuring out what math you had to do. Okay? It seems to be a common theme in this unit, and it will be for the rest of the course too. All right, questions on how that one worked? All right.